Hi, and welcome to our new chapter here on risk minimization in our lecture on Introduction to Machine Learning. So I guess you can decide yourself whether you find this advanced or not so much. So this is our first session here in this chapter. So here I'm going to recap risk minimization and empirical risk minimization in a, I don't know, maybe slightly more formal way. We have seen this principle again and again in the previous chapters, but I kind of want to recap it here. And then we are going to do somewhat more of a, I don't know, slight deep dive into this. I'm going to establish a couple of more theoretical concepts like what is a base optimal model, what's a base risk, what's stuff like, I don't know, a risk minimizer, what does population minimizer mean, what's base regret, estimation and approximation error, and some various ways of specifying either optimal constant models or optimal conditional models, which I guess we are more interested in. So optimal ways of predicting an outcome given some feature vector X. And I'll wrap up by super briefly discussing things like mentioning a little bit things like consistency and universal consistency. Okay, I guess let's start. So like I've said, we have seen things like empirical risk minimization quite often before. What does this mean? So this means, given some data here, and I guess I'm surprised my pen tool is working. So given some observations xi and yi, we have a keen interest in learning a prediction function f which maps x to y or to some form of a score which describes y, okay? My latter comment is a little bit more interesting or relevant if you're talking about a classification, when we might be predicting, I don't know, decision scores or probabilities or hard labels. So for this session here, I guess it's a little bit easier if we mainly think about regression here. I guess that's going to be my background context for now and for a couple of sessions in this chapter, and then we'll switch over to discussing classification. So so we have some data, xi, yi, endpoints, and we want to find a mapping f which maps our feature vectors to our outcome so we can predict y, and we want to do this in a loss optimal way. Okay, there's going to be some loss function L, and this loss function here operates, it's a bivariate two-argument function. So the first argument is going to be our ground truth label, and the second argument is going to be our score vector. So for now, just imagine that this is, so y is the set of real numbers, so we're in regression, and our prediction is also some real value, so it's on the same unit, on the same scale as our measured outcomes. And in classification, this r to the g might be a g-dimensional vector of probabilities or a g-dimensional vector of scores. I don't want to go into this now. And this L function is simply going to measure the error between our ground truth label and our generated prediction from our model. And it's going to be some form of a distance between these two guys. Say, it might be something like a squared loss, squared distance, so absolute loss or something else. This is our model here. So maybe I should have started out with this. So our model maps a feature vector to such a prediction or score vector or scalar, and our model lives in some form of a hypothesis space, and that's just a fancy term of saying it's this set of all functions where every admissible function is in there that we want to optimize over or pick from when we numerically learn, so to speak. And when we are trying to find the best fitting, best matching function to our data set. And our way of doing that, at least empirically, is exactly this thing here. So this empirical risk minimization formula, which simply means in order to pick an f from our hypothesis space, take a certain candidate, loop over all of your data points, your pairs xi and yi, now compare the ground truth label yi with the generated prediction f of xi, measure this loss, measure this distance, sum it all up, and this gives rise to a certain risk value, some numerical score that we associate now with our candidate in model F, and that score is going to describe how well it is encoding how well our model F reproduces the observed labels. And I guess that's a good thing then, in order to judge the quality of a model F. And if we have such a score that we can, or such a risk value that we can identify with each element in our hypothesis space, we are now very close to like optimizing over our hypothesis space, minimizing this, and yeah, operationalizing data-driven learning, so to speak. Now, our data is assumed to be somehow probabilistically generated. So it comes from some underlying distribution. You might also call this a data generating process, but it's kind of, I don't know, maybe some fancy way of saying it's generated from some joint distribution over X and Y. And our usual assumption is that our data is generated from this distribution capital Pi in some capital P, in an IID fashion, and that means it's independently and identically distributed. Yeah? So they all come from capital P, and they're all independent, and that's going to be our setting for not most of this lecture, but pretty much all of this lecture. Of course, you could also define a theoretical version of this empirical risk, and with theoretical, I don't know, we just mean that we are now not minimizing this over some given data. We're minimizing this over this distribution guy, capital P here. So this, theoretical analogon, so to speak, is pretty much just saying, hey, we consider expected loss now. So compute the expected loss for a given model F. You now compute the expected loss over our given distribution, capital P. Yeah, and that's here just the longer way of writing down this expectation, right? And that theoretical risk is, I don't know, what we're actually really interested in. Yeah. Unfortunately, we usually can't work with that. We can consider it mathematically, and we will. But in reality, very often we have to resort to this thing here, because we'll assume that this distribution is unknown to us. Even its form might be unknown to us, and we proceed in a, I don't know, I guess in a non-parametrical way of estimating F now on data without assuming too much about our data generating process. Here are two examples to make this a little bit more concrete. Very simple example. Maybe we are looking at a linear model. Then our hypothesis space is, well, I guess the set of all these linear functions. I don't know, maybe with P features, because I don't know, our input space is p-dimensional, and there's like an intercept here, and maybe our loss function to optimize this thing is, it's usually going to be like squared loss. I could deviate from that. We'll do that here also in this lecture and study the effect of that. But traditionally we would minimize squared loss and what that means, and how our, I don't know, space of alternatives looks like, and what the implication of changing this would be is pretty much one major topic here of this chapter. That we could now solve by empirical risk minimization. And here's a second pretty common example. So our model might be a multi-layer perceptron. So here, this would be a neural network with one hidden layer. Just, I don't know, chosen that as an arbitrary example, with rectified linear units or as activation function. And we would maybe use something like cross-entropy loss to optimize that. And here's just, I don't know, the hypothesis space. I guess that's somewhat redundant of, I don't know. I just wanted to be complete here. But I guess you can kind of see that immediately from the model formula here in this first line. Yeah, and this cross-entropy loss, you might also call log loss or Bernoulli loss. And what all of that means and why all of this is equivalent is, again, part of this chapter, but not of this first session. A few very, very brief words about hypothesis spaces and about the parameterization. So, well, like I said, our hypothesis space, capital H, is just a set of admissible functions that we want to learn over and want to pick from when we optimize. So you have to define this somehow. Yeah, and a major part of machine learning is like creating interesting sets now that have certain properties. What I want to say here is that this risk function I'm going to define this as a mapping from a function to a risk value, but I could have just also pretty much equivalently said it's a mapping from a parameter vector to a risk value, because I'm usually going to assume that this space, this hypothesis space over our functions, that is going to be something like a, I don't know, an indexed family of function, a parameterized functional family of a parameterized set of functions where our parameter vector is this theta thing here, and that theta vector simply fixes our function. Yeah? And the reason why we're doing that is because very quickly we want to operationalize what we mean by learning. Learning means empirical risk minimization, yeah, at least in a practical sense. And that means we want to optimize this over, we don't really want to optimize over spaces of functions. Could do that theoretically. And I guess, I don't know, maybe gradient boosting is doing this a little bit more. But in general, what we want to do is we want to operate on vectors, on preferably even on numerical vectors, because we want to do things like gradient descent, and applying things like gradient descent, or applying things in general like numerical optimization to the ERM problem is in a certain way, or I don't know, concrete way of implementing what we mean by learning on empirical data. So it's operationalizing machine learning. Yeah, maybe one last caveat. So for some model classes, some parameters might actually encode the same function. So this mapping, when we go from parameter vectors to functions, this is not necessarily injective. Yeah? So two parameter vectors might give rise to the same function. This is potential concern to us if we are worrying about inference on these functions, and with like statistical inference, interpretation, so to speak. And this is usually called the non-ability problem. I don't care about this here, so I don't want to go into this for now. We are currently mainly caring about finding an optimal function with respect to the ERM principle and what that means and how we're going about that. So let's take a breath. Let's consider this, loss minimization problem from a mathematical perspective for a few minutes. So I want to slightly change things now, not a lot. So I'm just going to assume that there's some random variable, which I'm going to call z here. And that's from my label space. It could be from some arbitrary space, but for me it's mainly labels that I'm interested in. And it's distributed somehow. So it might not be, I don't want to immediately now associate that with the label distribution. I'm just going to say that this is some form of a random variable. It has some distribution. And the thing is, I want to associate with it a couple of different distributions later on. So I want this to be pretty flexible. And the type of problem I now want to consider is that, how about we look at what is the expectation of a loss measured between this random variable z and some constant c. So the idea is, can we talk about an optimal sense? Can we talk about an optimal constant, which is loss optimal, when we associate it with that distribution in expectation? Yeah? So in a certain sense, given that loss function, what is the best constant c which characterizes this function, or that we can associate with this function under this loss function? So what is the constant that approximates z with minimal loss? And that's going to be our question for now. And what I want you in a few minutes to consider for this distribution Q are three, I would say, interesting scenarios. So one scenario is going to be Q is simply the distribution of our labels. So the marginal distribution for y of our data generating process. And when we now consider this problem here, that pretty much means what is the best constant in a theoretical sense to reflect, to be associated with our label distribution, yeah, to represent our label distribution without considering any features. Yeah? So I'm going to call that the optimal theoretical constant prediction. Yeah? The optimal constant model, yeah, under theoretical risk minimization. And then, of course, there's the empirical version of that, where we're observing n labels, and again, we are forming some empirical we're going to perform some constant prediction. So what's now the best empirical constant we can associate with this vector of all of the observed labels in a loss minimal sense. And even more relevant to us, because we're interested in prediction, right? Interested in predicting y given some features x. We could also assume that our distribution Q here is a conditional label distribution given x, given some feature vector x. Yeah, so x is going to be my random variable. So that's usually here, or yeah, I'm denoting here random variables in lowercase. And if I have to like use random variables and I don't know, observed or non-random point vectors, I'm going to denote that with an x tilde. Yeah. So, and this thing here, if we consider that will give rise to a pretty important concept in prediction, which is going to be the base optimal pointwise prediction, or the theoretical risk minimizer, and defining what that is and understanding that a little bit is going to be a major goal of this session here. So, yeah, let's maybe connect that a little bit with what you may or may not know from statistics. So if you don't know this and have not heard of this before, don't worry. At least I want to enable you to, or make you aware of this connection, so later on you can study this a little bit more. It doesn't matter if you have, if what I'm going to do on the slide here is news to you. It's, yeah, all of the remaining stuff is, I guess, accessible without having seen this before. But because many people don't know this, at least I want to mention this connection at least a bit. So if we associate some value with a given distribution, and it doesn't necessarily need to be in this form here. So this is now a pretty general concept. So we could say there's some, I don't know, some function t, which associates some value with a given distribution, capital P. This is usually called a statistical functional. And that's just fancy terminology for saying, yeah, I want to, I don't know, associate some form of a characterizing value with a distribution, and it's generalizing things like expectation, median, variance, and so on, because all of these things, they are associating values with distributions, and they are like somehow describing and characterizing a certain aspect of a distribution. I guess I would hope that makes sense to you. And this is just a, I don't know, generalizing terminology for that thing. And now if this, well, some of these statistical functionals, actually quite many of these, can be specified in the form of solving some optimization problem, solving a minimization problem. So the median, for example, is the best constant approximation of our given distribution under L1 loss, under the absolute, under a distance measured by the absolute value. The expectation, or the formula of that, you can easily write that down, right? It's just like something like this here, right? You can also turn this into, or phrase this as a minimization problem. It is the value that is closest to our distribution under L2 loss. Now, if we generalize that and say these statistical functions that we're interested in, they can be written as this loss minimizing problem. So this is the C value that is minimal when we compute the expected loss between our random variable z and our constant c. And something like that is called an M estimator in statistics. Some people call that thing here already an M estimator. And some people say, well, it's an estimator, so I guess we should do this empirically. And then they call this thing here an estimator. So I'm going to call both things an M estimator, and the M, unfortunately, also a little bit vague what that means. Some people say that this means maximum likelihood type. I guess a little bit more intuitive if we say it means minimizing, like solving some form of minimization problem. And this was invented by Huber, pretty famous statistician who was very much also interested in robust statistics in the 60s, I guess around 64, 65, I've got the exact year. Yeah, and as you can see here, this is very, very, very close to our risk minimization principle. Yeah, so that thing here, the first thing here is very close to that theoretical risk. It's not close to it, it's pretty much it exactly. And this thing here is the empirical risk minimization. And this here only talks about, I don't know, approximating constants. But if you pick as distribution Q something like a conditional distribution, it immediately turns this thing into talking about like optimal predictions based on feature vectors. And this is exactly what I want to do here in this session and the next ones. So let's just like look at the same thing from a very, very slightly different perspective. So these constants here that I just considered on the slide before, so these unconditional constants, you could also see them as some form of a constant baseline predictor. So maybe you have some data, maybe it's a machine learning problem, and you're going to fit some pretty complex type of prediction model on that. But maybe you also want to ask yourself, hey, what happens if I use the easiest, simplest form of a model available to me? And that might just be a constant model that is not acting on observed feature vectors at all. So it's a featureless model. It always predicts the same value. And you can see this as a baseline, right? And you can measure its performance. And if a more complex model is not better in terms of, I don't know, training error, later on probably more test error, or complex model is potentially garbage, not very useful to us, and maybe would even say that if we can't beat that in general, we maybe can't even learn a lot from the underlying distribution that our data comes from. And talking about these, what I want to do in some of the upcoming sessions is studying certain types of loss functions. I want to derive these optimal constant models because, well, we will also say they will pretty much directly enable us also to understand something about the conditional distribution, so risk minimizers and optimal predictors, and they will give rise to optimal baselines, and they're sometimes also useful as, I don't know, components and algorithms, as optimal intercepts, so I don't know, starting points and algorithms. So in general, it's quite useful to simply study this question here. And this thing here, and this is exactly what I defined on the slide before, so I haven't, I don't know, generalized that or extended this here in the slide, just on this slide. And we have also looked at this before, so this is just the empirical version of this loss minimal constant. Yeah, let's make the scenario a little bit more interesting. Let's talk about optimal predictions. So I want to now define what is usually called the risk minimizer. Some people also call this the population minimizer. Some people call this the base optimal model. And what we mean by all of these terms is that we don't want to currently consider a certain specific hypothesis space, and practically we usually have to do this in machine learning, but from a theoretical perspective, we want to currently simply consider an unrestricted space. So I'm going to denote that by this H all here. So this means it's the hypothesis space of pretty much any measurable function that exists. So this is maximally large, so to speak. I will also assume that I have access mathematically to my underlying data generating distribution. And if I now define, or I'm going to call now the model from this unrestricted hypothesis space, the model F, which has minimal risk. So that's the measurable function that is risk minimal. This is what I'm going to call the risk minimizer from now, or the population minimizer, or the base optimal model. So this means go over this space of all admissible function, consider the theoretical risk for all of them, which is the expected loss, which you can also write equivalently in this lengthier form here as an integral. And this optimal function in this theoretical space from this maximally largest space of all measurable functions, that's the risk minimizer. This is as good as it can be. No better model can exist, at least in a theoretical sense. And the associated risk of this optimal model, and for theoretical optimal, I will use a little star to denote that. So F star is my optimal model. And the associated risk I will denote with an R star, and that's called the base risk. Okay? And there's never going to be any model that can, significantly outperform the base optimal model with its base risk or base optimal risk. So in terms of notation, star means I'm minimizing the theoretical risk and not the empirical one. And sometimes I want to talk about like an optimal model from a certain hypothesis space, and then I'll put that as a subscript into this F. So here I have an H all, which means I go over the space of all measurable functions. And when I want to speak about minimizing the theoretical risk over a certain concrete constrained hypothesis space, we'll call that the risk minimizer within that H. And especially now here, pretty useful that we now put the H, the hypothesis space, as an index, as a subscript next to our F star, so we know which hypothesis space we're actually picking from, which we are optimizing over. How about we now think about how such minimizing model, such a population minimizer might look like, and whether we can potentially get our hands on a, characterizing formula for it. So let's just start here with our theoretical risk. I'll just write down here its definition. So there's nothing new in here. So this is just expected loss now. Now, we can use this very useful tool of the law of total expectation to unravel this a little bit. So on the outside, we're now going to take the expectation over x. And on the inside here, we're going to take the expectation over y given x. And the law of total expectation tells us that these two formulas here are very much equivalent. So on the inside, we now have here this expectation, the conditional expectation of this thing here. So the loss of y between y and f of x. And it's conditional because it's conditional on x. So the inner part is a random variable itself. And through the outer expectation going over x, we now integrate this out completely. And that gives rise to our expected loss over our distribution, so our risk value. And as we've said before, that was our major starting point. There's pretty much no restriction on our function f. So we're very much free in, constructing that. And that means we can pretty much construct this pointwise, right? So we can now say, hey, how about we look at some arbitrary x, or in terms of, concrete numbers, some x shouldn't be an x bar, it should be like some x tilde. So we look at some point x tilde, and we can assign any output to our model f. So why don't we just do that loss optimally? And this is exactly what we're going to do. So for a fixed feature vector x tilde, we will now define the output of our population minimizer or some function f star as the solution to this conditional loss minimization problem. So where we compute the conditional expectation of the loss between y and some constant c, and that's going to be output that we prescribe to f star, given that we are at the feature vector x tilde. Now that this x tilde vector is our vector of observed features. And if we construct our model f star in such a way, that this here is at each point x, any arbitrary point, the prediction is this loss minimizing value, then it's very obvious that this is the best loss optimal model across the whole distribution, right? It must be like that, right? If it's loss optimal at every point, it must be loss optimal overall. And we are, because we have no restrictions on our functions, we can just construct our function like that. Yeah? Which means we now have some, still somewhat theoretical, but we have now some handle, yeah, on how our population minimizer actually looks like. And later on we're going to dive into this a little bit more deeply if we then specify which loss function we're using, and we can actually like construct concrete formulas for how such a optimal pointwise prediction looks like, and we'll see that in quite a few of the upcoming sessions. Okay, this base risk minimizer and the associated base risk, that's mainly a theoretical tool. As said before, in practice we need to restrict our hypothesis space for efficient search, and for many practical and theoretical reasons we have to operate on a restricted hypothesis space. And also, I've said before that we usually don't know our data generating process, so we also can't solve, theoretical integrals, theoretical expectations over such a given distribution. So in practice, we're going to use ERM, empirical risk minimization. Not going to repeat this formula because we have discussed this now many times. You can now think a little bit about, does this, empirical risk, does this give me any theoretical guarantees? So there's one positive thing to say about this, and that is that if you're considering a fixed model F, so you're not like minimizing that through ERM, it's like it's fixed, you have somehow picked this already, and now you take a look here at this empirical risk, or you have written down the average version of that, so sometimes call that R bar, and just dividing by sample size n now. And this thing here converges to the true risk if we are willing to let our sample size go to infinity. So this converges in distribution to this true risk. It's a consistent estimator, therefore, it converges to our risk if sample size goes to infinity. So this is what we usually call a consistent estimator. That doesn't necessarily imply that the selected ERM minimizer converges to our theoretically optimal population minimizer F star, because there might be overfitting going on, and we need some forms of like concepts of uniform convergence. So we need a few more assumptions on our hypothesis space, and we also would need a little bit more of mathematical machinery to describe these things. So this would be content of a more theoretical statistical learning lecture. I don't want to go into this here now. I will not pursue this line of reasoning much further here, but I want to mention this a little bit. What I do want to do is I want to decompose my risk now a little bit. So I want to introduce now what I mean by estimation and approximation error, and that's actually a very simple concept. I think it's enlightening, it's helpful, but the mathematical construction is extremely simple. So I want to consider the scenario, which is very realistic, where we have some constrained, restricted hypothesis space H, and we are now training our model with ERM. Well, we could consider now its true risk. That's certainly of interest to us, right? So what is its empirical risk? It might be overfitted, might be close to zero, but there's going to be some true risk, some true expected loss over the data generating process. So let's look at that. And, you know, I don't know, somehow, I don't know, normalizing that by subtracting here our base risk. And this delta, this thing here, must of course can never be smaller than this guy here, right? Because R star is defined by F star, and F star was supposed to be optimal, right? So this thing is certainly non-negative, yeah? But usually, because we do empirical risk minimization and we act on a restricted hypothesis space and not an unrestricted one, it's going to be, yeah, positive, yeah? And this delta, this excess risk, so to speak, yeah, I'm going to call excess risk, or I'm going to call it the base regret. Yeah? So that's the, I don't know, the difference we incur by working on finite data empirically and working on a restricted hypothesis space. And that's already my decomposition I now want to apply. So this difference here, I'll slightly extend by introducing a zero. So I'll do a minus plus of the same thing. And this same thing here that I'm plugging here into the middle is the infimum of the risk of any model picked from my hypothesis space under consideration H. Okay, so that's the associated theoretical risk for the best model I could pick from H. And the only thing I'm now going to do is I'm going to look at this thing here, so this first term and this second term, and the first term I'll call an estimation error, and the second term I'm going to call an the approximation error, and the first term I'm going to call the estimation error. And that actually makes a lot of sense if you think about this a little bit. Don't have to think about it too deeply, because I hope you're going to agree with me that this is somewhat intuitive. So let's take a look at the first term. So here we have the difference between the theoretical risk of our F hat model, and F hat was fitted on finite data, and that's what the hat means, via empirical risk minimization, right? So that means if we are in a hypothesis space H, we're going to find the best model, yeah? Not theoretically best, because we're not optimizing over the true underlying distribution, we're optimizing over concrete finite data. And we're doing that with, I don't know, numerical optimization, which is also not going to be perfect. I don't even want to go into this here. We could actually make this decomposition a little longer to reflect that, and I guess I'll do that in a later session here in this chapter, but I don't want to do this now. So for now, it's enough for us to consider that we're working on finite data, right? And therefore, we call this the estimation error. Yeah? So this is the difference in theoretical risk by A, operating on and minimizing over the theoretical distribution, versus B, doing ERM on finite data. That's why it's called estimation error, and you can see that here in this somewhat abstract figure above. Okay. Now the second term here is called approximation error, because I'm now considering the difference between the theoretical optimal model picked from my restricted hypothesis space H versus I'm going over the unrestricted space. Now, so I'm minimizing the same thing, but for this guy here, I can really use any type of function from an unrestricted space. And for this here, I have to pick from the space of, I don't know, all neural networks, all linear functions here, so that might be severely restricted. And my optimal model with an, I don't know, optimal functional form, optimal shape, might not even be in this space. And this was reflected here. You can see this here again in the figure above. So I might not even be optimizing over the correct hypothesis space, unfortunately, if I'm unlucky. So let's wrap this up. I think this session was already long enough. So I want to mention briefly what we mean by consistency, or consistent learners, or universally consistent learners. So this is an asymptotic property. It's an asymptotic property of a learning algorithm, and it ensures that our learning algorithm pretty much returns the correct model when given unlimited data. So given some form of learning algorithm, so learning algorithm for us is some mapping from a data set of size n to an element of our hypothesis space. Yeah, so training data goes in, some learned model comes out, and yeah, so this estimates a model f hat, right? It picks a model, usually through empirical risk minimization from our hypothesis space. And we will now say that our learning method I, and it's called capital I, I've said this before because it's a inducer, is a fancy name for learning algorithm, and we are saying this learner is consistent with respect to a certain distribution if the risk of our estimated model f hat converges in probability to the base risk R star when n training data set size goes to infinity. Yeah? So if that happens, we are calling our learning algorithm to be consistent with respect to a fixed specified distribution capital P. But we usually don't know P. Yeah? So if we don't know P, consistency doesn't really help us a lot to choose a certain algorithm, a certain learner for a specific task. So therefore, there's this stronger, more general concept of universal consistency. We're going to call a learning algorithm, I shouldn't say algorithm, I should say learning algorithm universally consistent if it's consistent for any distribution. And obviously that's a way stronger concept. Fortunately, there are quite a lot of learning algorithms that have this property. There's a very famous consistency theorem by a guy called Stone, again, a very famous statistician, where he showed this for a certain class of weighted average estimators. So this is in pretty much k-nearest neighbors. And he showed universal consistency for this class of learning algorithms. And since then, we've been able to construct many proofs for different machine learning models that they have this universal consistency property. So I would say, yeah, I'm not sure whether I want to say like any machine learning algorithm of interest always has that, but yeah, like all of these powerful non-parametric learning algorithms have this. So support vector machines, artificial neural networks, yeah, certain variants of boosting algorithms and so on have this, yeah, which makes them quite powerful. Makes them also somewhat data hungry, and yeah, as I've said, if they have this property of being consistent for any type of distribution, we call that universal consistency. Okay. I could say more about this. Probably I should not, because I think this video has already been long enough. Yeah, I guess that was an important session here in our new chapter, but I will end things here. I hope you enjoyed this. See you in the upcoming session. Bye bye.